Hi everyone. Okay, how have you been? Well, even though I made an announcement about being late on this uploading of lectures, that I originally said that I will be able to put them up by the as late of the midnight. Actually, there was a yesterday, but a lot of things actually, additional things that I need to fix. So, been taking so much more time, so I am only able to start this recording again. So just bear with me. Sorry about that. So the next this lecture, which is not next, this lecture, which was actually newly included part starting this semester. In previous semesters, I did not have this particular topics assigned, dedicated for any lecture. Although in the chapter 2, I set up a little bit of the time to quickly go over about the basics of some of the chemicals, because chemistry of life, because otherwise that's impossible, almost impossible to freely go over about all those other more complicated aspects about the genes and biochemistries and the cellular the function and structural aspect. So, and also at the same time, I am aware of that many students taking this course are just purely non-science major who have never taken in their previous lives and taken any science course. So for them, throwing a lot of those chemistry, which is actually very essential to understand the framework of all this biology. Once again, let me reiterate this. Life is chemistry, yes. So, however, still going over so little details about this chemistry of life would be too much torture for this non-science majors. So that's the reason why I've been trying to avoid as much as possible to discuss the chemical aspect of the life science until now. But for one of the reason why this semester I decided no, I cannot really do that anymore, and then let's just include some major part of this life chemistry, is because among many other things, that as this whole the life science and information also becomes more and more complex, just like take the similar example in the case of this computer science. So everybody here these days talk about the codings and all kind of different things in those areas. Just like that, in life science too, many more complex things casually are talked about, just like a regular topics of everyday lives. And most of those actually people cannot really grasp real bottom line without understanding the chemistry of this life science. Otherwise, if you simply avoid, like pretend that there's nothing about chemistry, and then simply pick up the surface of this all newly emerging information, which are all very important to your lives, then you are actually simply not doing any service to you, because that would be just simply picking up and then trying to memorize a little piece of the information, which are in an overall scheme, which is a totally absolutely have no point at all. So that is the reason why I decided to go over. But nonetheless, what I'm trying to do is I will try to go over quickly and I only pick up some of the very essential things that is ultimately absolutely necessary. So try to squeeze them down so that I can finish all these discussions within the the boundary of 1 week worth the lecture. Let's try that. Uh, I'm not really sure whether I can successfully accomplish that one or not, but okay. Uh, so like I said, there's like this chemistry, which means if you think about all different the parts uh, that are integral to yourself, whatever it is or whatever whoever you are, that actually if you zoom in and then dig in and think really think about it, what they are made up of. Basically, if you just go deeper and deeper at the base, you'll find that the individual, the smallest unit of this conceivable organization lies an atom. So all these materials are made of different type of atoms. Okay. So why are we doing this? Actually, the basic ultimate goal of this chapter's content is to be able to understand the basic components that constitute the life, which means in particular the macromolecules, right? So to understand the whole thing, still we have to invite the approach of reductionism in efficiently trying to understand the scheme of life. So to do so, for example, if you want to really know about what's going on in our life, like basically in the cell, you better actually be able to understand all these different macromolecules. So that is the reason why. So here we are taking an example of, for example, this a cell. Sorry for not taking an animal cell as an example here, but because the plant cell had this one additional structural boundary, which is a cell wall, which is made of some specific macromolecule, a carbohydrate actually, which is a cellulose, but it is a type of carbohydrate. And also you can see many different types of internally inside of this structure. Will you find many different components? Each of function is extremely important, and better yet, if you want to understand each function, actually you better be able to understand all those chemical nature with some a little bit of the logical the foundation coming from the physics as well. So bottom line is there are 4 different types of macromolecules here in life. 4 different types of macromolecules, including protein, carbohydrates, lipid, and DNA and RNA altogether. We usually consider them as nucleic acids. So all this. But if you really think about where they come from, it all started from smallest unit of an atom. And an atom get together, two or more atoms got together to build the molecules. Okay. Here, what it takes is the bond, chemical bond. So we have to be able to understand what types of chemical bonds is there. Okay. So that's one of the other goals of this chapter. And once you pick up some specific chemical bond to synthesize specific molecules, now what it takes is all these are the examples of such the macromolecules, so to speak. All these macromolecules, which we should just say this is an organic macromolecule. So to build all different kinds of macromolecule which are organic, then what you need to do is you have to do this starting from the so-called specific monomer to assemble a specific polymer. So these are as the result of this the build-up process of from monomers to polymer. Okay. These are also, of course, a kind of we have to use some specific skills of chemical bond building, right? So these are the basic goals of what we want to take a look at and then understand in this chapter. Okay? Having said that, all these atoms, what are atoms? Okay. They are, well, of course, there are in the atom. We have so many different small subatomic particles. The identity of many those subatomic particles have not been known even when I was taking the college physics some time ago as a freshman or a sophomore in my college here there in the United States. Okay, mind you, I didn't take any college physics or anything like that when I was in. I was the social science major in Korea. I was an economics major, and then after 3 years of the wasting time, I finally decided to switch into something more stupid field like this biology. That's here I am. So anyway, all these materials are basically are made up of a smallest unit called an atom. They are the basic the organization unit, which still carry the property of individual different elements, so to speak. So, like we do have so many different types of elements, each of which carry its own unique chemical and physical property. Okay? Hydrogen, oxygen, carbon, they are all different examples of such elements. Okay? So if you break, it is possible to break each different element into much smaller subatomic particles, but then you lose all its unique elemental chemical physical properties. So, and it doesn't really we don't really have to worry about anything like that, because here in biology the kind of a degree and amount what it takes to carry on the understanding of biology is very elementary and minimal. So we are not going to talk about two really real serious physics or chemistry here. So here about on Earth about 100 naturally occurring elements do exist, although in the laboratory some other additional new kind of elements have been synthesized, just like alchemist, mind you. So, and all these different elements were nicely arranged, organized according to their certain specific chemical, physical rules, which is called known as the periodic table, isn't it? Uh, so some of you who are the science major might have to be forced to memorize all this periodic table when you were in high school, so anything like that. But at least for me, it doesn't work because no matter how hard you try to memorize, I have never tried even, but probably you will just keep forgetting about anything. So here they are. The only reason why I am showing this periodic table is these are the whole examples of such different types of elements existing on Earth. And the reason why they are arranged in this way is because it is for the sake of a convenience. If we do so, probably it's much better to understand certain specific rules over there according to their unique the properties. Yeah, for example, the one arranged in this column all have certain characteristics in common, and so is this column's elements, and just like that. So that's one of the reasons why we have this type of table-like arrangement. Here, this figure showing only partial part of the periodic table, but the point here that this figure is trying to make is what? Guess what? Just by looking at this figure carefully for a moment, should be able to get the message what this picture is trying to portray. That is one of the actually way personally I my approach of learning the information knowledge in biology. I used to practice this way. I try to, instead of starting reading the whole sentence first, I first try to look at the figure, because figure is the one that summarizes the point of what has been written in. And in many times, more often actually than not, I was able to understand the message just by looking at it and trying to. When you try to explain yourself, explain what the figure is trying to say or describe, then it is really, really helpful to even organize, to get your idea organized about that particular fact. And also, it is very like efficient way of delivering what you know about this particular information. But anyway, getting back to this business, here what seems to be the message on this figure is that even though you have so many different elements, just like as I showed you in the previous slide, that there are like about 100 different elements, but in the integral part of your body as a life content, the type of elements that have been included as part of your life is not really that many, all those different variety of elements, but only a very handful of small number of elements are exclusively like become parts of lives. Notably, like these four. Among these, actually, one is more noteworthy element is this carbon, because all others, like hydrogen and oxygen and even nitrogen gas, they are relatively abundant in other area, like not only inside of the life body, but other areas. All these materials are plenty. So, like by the rules of this proportion, one can assume that that is kind of a natural, reasonable that you are able to find so much such element. But carbon is such an exception because the amount of carbon available outside of the living system on Earth is not really that much. However, nonetheless, you have a really significant portion of your body, or whether you are as a human or other types of life, including plants and fungi or even bugs and bacteria. These carbons takes a very significant portion of your. So, like, if you look at this distribution chart, of course, in an oxygen and all this hydrogen and all other among all other abundant element, but look at this carbon takes up almost like 20% of which is very significant amounts. And probably you have already know the reason why. As carbon, why there are so in terms of this proportion, there are so much carbons are in the life forms only because carbons are the essential, the integral part of the central element to build the macromolecules around it. Otherwise, without carbon, that's why the carbon is something that at the center stage of all these molecules we call as organic. Yeah, the term itself, organic, is something very suggesting what it is. So the basic structure of an atom consists of for all different elements, all of which are organized as an atom in structure, and that structure consists of one central part called the nucleus, including the proton and neutron, and the electrons orbiting, sort of moving around at the center of the nucleus, having that proton and the neutrons. That's the basic the structure or aspect of an atom. So, and number, depending on different elements, how many protons or how many electrons, how many neutrons does an element has differs. However, in a given element, the number of protons always is equals. I shouldn't say always, but generally, number of protein is equal to that of the neutrons in the nucleus. So if you have 5 protons and you have 5 neutrons, and actually another thing is the number of electrons are also the same. And the significance of this is the protons are positively charged in nature, chemically, physically, and electrons are negatively charged. And if the number of the protons and electrons are the same, then basically, in general, all these elements should be electrically neutral. Yeah, that's what it is. However, that can be violated if there isn't any inequality. Like if you have 7 protons but you have 1 more electrons, then as a whole, then that element will become negatively charged. It become ion. Or if you lose 1 electron or 2, then you will, as a consequence, you will become a positively charged element or an atom. But then now we recognize them as an ions. So that's the difference between an element and an ion. Anyway, so this is the basic conceptual organization. It's not the real thing, but we can imagine as it is similarly. So in the central part called nucleus. So by the way, this is a description of such organization in the particular element called the helium, having 2 protons and 2 electrons and 2 neutrons, right? So this is the type of, so the electrons are moving outside the defining the outermost boundary of any element. Okay? So here in the chapter 2 lecture handout, I generate two different versions. By the way, this semester I particularly trying to actually emphasize that I am trying to jump onto the new era of all this lecture handout, etc. So they will all be very difficult. They are not going to be print friendly on purpose. Okay? Because kind of in recognition of the whole our environment around us are moving and changing into some new era. So let's try not to depend too heavily or much on the old traditional way of this getting things across. It's like whenever you have such material, you always want to make them print out and then try to look at them. Myself, actually, I have long time ago I have abolished such an habit. So as much as possible I try to utilize this electronic device. Of course there are some advantages and also the big disadvantages in that, and potentially and practically as well. But anyway, that's so with that in mind, I try to generate two different versions of the lecture handout material, and that is the reason why I had some like EPUB electronic books version, as well as high quality PDF, which is suitable for like a device, electronic device viewing, like on your computer screen or your like a pad, tablet, or even your small the mobile phone. And also the more traditional way of for those who, for many regions who have difficulty in getting access to such devices, still you can or you have to resort to the old-fashioned ways. For those, I also provide the so to speak classical way of such media material, so that you basically use in the printout. So this chapter, but then I try to incorporate some of those small movies. Then the disaster happened because the snowboard site did not allow the file size larger than certain limit, which was only 100 megabytes. So for all those materials, I was not able to upload directly on the snowboard board classroom site, so I had to provide on a link. And also I provided some of the more detailed the explanation about how to use. So some of those larger file size material, the reason why they are so big in size is because of this embedded movie, which is I took from some very good reference book about the biology, and then regenerated by the screen recording myself. So I had to do some really extra work of mine. Whether it will be such a useless, silly business or not, it will just totally up to you. But anyway, I will keep trying this. So for those who were able to get access to this the higher, the bigger size file version, you should be able to handle on your own. So I don't have to go over this movie on my lecture. But at least for now, for those who did not have any opportunity to enjoy such, I will just here quickly. Hey, what's going on? This stupid.
Adam.
Huh. Once again.
Atoms are often visualized with electrons surrounding the nucleus like planets around the sun. The element helium has two negatively charged electrons surrounding a nucleus containing two positively charged protons and two neutrons that have no charge. To understand chemistry, you need to understand that atoms are three-dimensional, and that electrons have a unique way of filling space. Electrons move at nearly the speed of light, moving that fast while being confined to an area as small as an atom by their attraction to the nucleus. It is as if they are everywhere at once in the tiny volume of the atom. For that reason, it is useful to think of the electron as an electron cloud rather than a particle. If we showed the nucleus to scale, it would be too small to see. Essentially, all of the volume of an atom is taken up by the electron cloud. When atoms meet, their electron clouds do not combine but bump against each other, unless a chemical reaction occurs.
Okay, so what a neat English. The bottom line about this, the take-home message about that short movie, was that actually the electrons that something like it's very difficult to comprehend their movements, rather than we have a defined path, but actually electrons move around and generate some kind of a fuzzy cloud-like the overall path is probably one point. So this, getting back to the basic structural aspect of its atom. So there is an atomic, each different atom has own unique atomic, so-called atomic number, which is equal to the number of proton. In some books it describes as defines the atomic number as like number of electrons, but in that case, if that element becomes an ion, then the atomic number should change accordingly. So that is not the correct way of defining the atomic number of an element. So I will stick to that number of proton equals to that atomic number. But then there is another definition which is about atomic mass, which is like how heavy that atom it is described by the atomic mass parameter. And so here the number of proteins added together with that number of neutrons defines any specific atomic mass. Hey, what about the electrons? Maybe electron might want to protest but in reality the electron is so light, it doesn't make any slightest difference, so it's negligible. So in calculating and defining the atomic mass value, electrons are totally excluded. This is only sufficient and good enough for distinguishing all different types of atomic mass. So in the case of carbon, the photograph of charcoal is seen over here. So the number at the bottom indicates the unique carbon's atomic number, which is 6, which means we can understand that carbon has a 6 proton and also 6 electron as well. And the 12, which means that we can understand, okay, if the number of protons is 6 and here this particular carbon's atomic mass shows that 12, which means you have exactly the same number of protons, because by definition the number of protons plus number of neutrons become this atomic mass. That's how you deliver and utilize the whole information. And so accordingly you have so many different parameters on different type of elements like this, as you can see over here. Okay, so why this periodic table of the element once again appears over here, a little bit of the different version. Okay, the reason why I put up this different type of periodic table is because, as you can hopefully see here, let's go over, like, on this surface area of the periodic table, usually that turns out that number of the atomic number is like almost exactly the twice the atomic mass is twice as the atomic number, which means the number of protons equals to the number of neutrons. However, if you go deeper and deeper, which means once you have noticed that, okay, as you move along, each element gain one more electron, one more protons, like that, so that they become heavier and heavier. And as you go to heavier elements, now it begins to show a big discrepancies between the number of neutrons and the number of protons. And so, for example, let's look at the case of this lead. This is lead. Okay, the atomic number is only 82, which means that there are 82 protons, but the atomic mass at the bottom, which is 207 or something, means you have so many more number of neutrons than the number of protons that what it seems. So that's what it is. So the point here I'm trying to make is, for those non-science major, the atomic the number of protons is not always equal to that of the neutrons in every different case of the case of different element. Sometimes it's different. Now, getting into the concept of so-called orbital and electron shells. The reason why I am going over this is because now eventually the whole purpose here is to show you the concept of the significance of the electrons on the particular level of so-called electron shell is the actual real reason why I am getting all this. So the definition of an orbital in electron is the path or the space which is occupied by an electron moving around the nucleus, just like electron cloud, right? So this orbit in reality seems more like a kind of fuzzy cloud, because it is a kind of a description of a probability along which a given electron has the highest chance or probability of being found. So, like more conventional way of describing this, we have seen this, the helium, atomic organization of the helium looks like this. However, in reality, as far as the electrons goes, the movement of the electrons will generate this more fuzzy cloud-like shape. So in trying to understand the electron orbit, which is like I said, that is the path along which the electrons will move. We do have so many, just like as this photograph shows. By the way, there's a really nice, cute shape of each differently defined the type of orbits. Yes, so many complex types, different types of, according to the level of energy level, so to speak. A given element possess, depending on how much energy does this have, several different levels of such electron orbits, right? So we have to try to visualize and understand such the orbit of an electron in a given element in this three-dimensional way, but our poor brain usually is very difficult to handle properly. So if you actually dissect many different types of the electron orbit at different energy level, there are, as you can see, so many different levels of different types. That's all I can say. I'm not a physicist at all anyway, so I cannot really pretend to know anything about physics. What can I say? However, good thing is we can simplify and sometimes even intentionally oversimplify this concept. So it's okay. It's okay even in reality you have so many different types of very difficult to understand orbit. But in practically speaking, you can simply assume each different orbit having this two-dimensional way of very straightforward level, each of which can be represented by simple the lines of a circle. So, like, as far as this trying to understand the definition of the electron shell, same thing can be applied. So these orbitals, by definition, these are electron shells are the one that having different energy levels of electron orbitals, which is practically very complex notion. However, we simply try to understand at the like a basic from the two-dimensional level. One thing we can easily understand is, okay, there are different types of energy level of electron shell, and several different levels. Just like in the building, you have the first floor, ground level, and the second floor and third floor. And the higher the level, it will take more energy. It will be harder for you to climb up. It's probably a similar analogy for you to be able to understand. So the energy level, so the closer, the lower energy level of a shell can be placed as closer to the nucleus, like this. So in the atomic nucleus, one energy level, the lowest energy level electron shell is there, and the electrons having the lowest energy can orbit around this shell, and the second energy level and third energy level, so depending on how many electrons you have, you can, like, depending on how many people you have in your group, you can have like just one story building and just be satisfied with, or you cannot function, so you have to have a 2 or 3 different story, multi-story buildings, just like that. So, and several different types of energy level shells can be imagined here, as you can see. KLMN basically meaning the lowest and the higher, and the higher the highest, so like you can move up from here to there, and the higher up to the higher level energy electron shell. Now the point is, so what's the point that I'm trying to make over here is, these different energy levels at each different shell, there is a certain, the maximum capacity of number of electrons that you can accommodate is, so the specific capacity is that what I'm trying to say. So there are only so many electrons in number that you can fill in a certain particular level of electron shell. Okay. So you just start filling up your electron, what you have, starting from the lowest level first. And then if that lowest energy level shell is filled, then you can move up to the second story and third. That's the way you can do it. And in reality, actually, incorporating the real, more realistic, this orbit model, this different energy level can be viewed in this way, and the thing is, each different level in orbit, there are certain number of electrons you can have, is because of the different types of electron orbit. In this box, as you can see, each box you can accommodate only 2 electrons in one box. But depending on what type of electron orbit you have, how many boxes you can have is different. So in other words, you have so many different levels of shells with the maximum capacity of electrons, all different at different level of electron shells also. Okay, that's the bottom line. That's all you gotta No. So like, let's take the example of potassium. This one should pronounce potassium, not calcium. Okay, potassium. And similarly, you should always trying to get the habit of pronouncing this as a sodium instead of a natrium, because I'm not kind of a pro-American, so I always try to like force anything more America friendly. No, quite the contrary actually in reality. But all this naming the chemicals already since long time ago, those international community have agreed upon to minimize all this confusion. So it is not all these English or American things, but that's the community, scientific community have agreed upon and then declared that, okay, from now on, we should start calling this element as potassium, not the calcium. That was like the reflection of earlier influence of the German science a long time ago. So anyway, that's what I'm saying. So I will always try to pronounce them as a sodium and potassium instead of a calcium or natrium instead. So anyway, take the potassium example. So you have 19 electrons. So to accommodate all these 19 different electrons, you will use first the lowest level electron shell can only accommodate the 2 electrons. And then you quickly fill up. Oh shit! Already it's 40 minutes, so I should just move up quickly. Always taking so much time. My apology. Here, this week's lecture, what I'm trying to is to have the lectures divided into smaller segments as one student have specifically requested it. So even if I did not reach to my the intended end of each divided sector of the lecture, I will stop there and then make that segment of the lecture even more fragmented, so that I can reduce the length of a particular lecture. So that's another thing that I ask for your understanding. Okay, so anyway, this potassium, the example of the potassium is just like that. So you just keep doing so, then eventually you will know how many different electron shells does this potassium need, is the point. So each different element, depending on how many electrons you have, so each different element will have different the electron shells of different energy level. It's the only thing that I'm trying to say. Okay. So here, electron shell. What's the most important about for us, the biologists, here is the electrons happen to be in the very outside, we call this outermost electron shell. Okay, this is the one actually mostly define the characteristic of that particular element. That the outermost electron shell we call as a valence electron shell. Don't ask me why the valence electrons on the valence electron shell is the one actually determining, but mostly one of the major reasons is those electrons are the most heavily affected by the energy status of a particular given element. And for every different element, all they trying to obtain, the ultimate goal is to reduce and to become the most stable, energetically speaking, stable being. Okay? So for that reason, the outermost electron shell, how many electrons are there and how can they reduce any potential energy? The potential energy is from the concept of so-called the quantum physics. Okay? So the more you can shed off your potential energy, the better. So that's all the direction of the all different elements to pursue. Okay, so so for example, if somehow the electrons are all filled up in the outermost electron shell, which is what the valence electron shell, and then that element becomes very stable energetically and will not try to do anything stupid. So they are called, for example, those are called, there is a group of on periodic table, those who achieve that goal of filling up all their electron shell to the maximum is called noble gases. So like, for example, helium and neon and argon are such an example of those noble gases, and these elements will be extremely difficult to get involved in the reaction. They're not very reactive because they don't have to. They are at the most stable, energetically speaking, status. Why would they try to do anything stupid? So this is like a bottom line of all these different elements. They will try to do anything to reach their own such status. Okay. Maybe we should just call them as their version of nirvana or anything. So the outermost shell, the valence shell, should be filled, and they will do anything, really anything, to get them. So this valency, with that, the definition of the valence electrons in a given element, how many more electrons does it take for you to become such like the valence electron shell filled, or like that type of a characteristic is defined as the valency of the element. So here, hydrogen, the valency, like in the case of a hydrogen, all it takes is just one more electron, because hydrogen is lucky enough to have the lowest electron shell. That is the only electron shell does it have. So all I need is just one. So the valency of hydrogen is just one. Okay. In the case of a carbon, for example, the valency of a carbon is 4, because in the case of carbon, the electrons take up to the second level of this electron shell, which requires 4 more. Okay, because at the outermost, the valence shell, the 4 electrons are currently occupying, so they need 4 more so that they can complete this 8 total maximum electrons on that particular electron shell. So carbon's case, the valency is 4, just like that. In the case of oxygen, the valency would be 2, because only 2 more electrons are needed to fulfill such a status. Like so, every different. We don't have to memorize all those different valency of different elements, of course, and simply understand why, because these differences in valency will actually be shown in the later on when we look at the different tendency of the chemical reaction in the chemical bond formation for each different element. So it is a little more extended version of such a valencies, like I just put it up here in my presentation version, just because it's looks nice, but the whole bottom line is, okay, different valencies, and what's valency? Is that all you need to understand? Okay, so probably maybe I should cut up that and then try to continue on this isotope in the second segment or something. So I have to cut up in between over here of the first session of the lecture.